You power on your classic Pioneer, Sansui, or Marantz. The dial lights come up, the protection relay clicks, music fills the room the way it always has. Everything feels solid until one ordinary evening it doesn't. A channel drops out. A low hum appears that wasn't there before. The unit locks itself in protection and just sits there. You didn't drop it, you didn't flood it, you didn't short the speakers, the failure just arrived. What almost nobody talks about is the thing that has been quietly working against that machine the entire time. Heat. Not the dramatic kind that melts plastic in a single afternoon. The slow, steady, invisible kind that builds inside every vintage solid-state receiver and integrated amplifier from the second you flip the power switch. After repairing thousands of these units, I keep seeing the exact same pattern. Prolonged heat exposure destroys capacitors, fatigues solder joints, stresses semiconductors, and eventually lifts traces or cracks boards. And the worst part, it stays silent the whole time. The gear keeps playing music while the damage quietly accumulates. That's the silent killer of vintage stereo equipment, and almost nobody sees it coming. 1. Identifying the silent killer. Heat. I've lost count of how many times I've opened a vintage receiver that still played music just fine, only to find the inside quietly cooking itself. Heat does not wait for you to turn the volume up. In these older designs, the real heat generator is the power supply board itself, and it starts working the moment you flip the power switch, even if the volume is all the way down and nothing is playing. Here's what happens. The big filter capacitors and rectifier diodes first create a raw, unregulated DC voltage that can swing all over the place. The regulator section then has to take that messy high voltage and drop it down to the clean, stable rails. The rest of the circuits need usually something like plus or minus 65V or plus or minus 35V depending on the model. That voltage drop is not free. The excess energy has to go somewhere. And in these linear designs, it turns directly into heat. I see it every week on the bench. The regulator transistors and the small capacitors clustered around them run noticeably warmer than the rest of the chassis, even at idle. Take the Pioneer SX 1250 as a clear example. Its regulated power supply board sits in a relatively confined area and has to dissipate a surprising amount of power just to keep the voltages rock steady. After a couple hours at idle, you can feel the heat radiating off those 220 packages. The smaller electrolytics right next to them are the first to show stress wrappers shrinking, tops beginning to bulge years before the big filter cans ever complain. I've measured the same pattern in Sansui G-series stabilizers and certain Marantz supplies. The heat is localized, constant, and mostly invisible from the outside. The original engineers knew this would happen. Their solution was pure convection. Hot air rises through the top vents, cooler air is pulled in through the bottom. In a 1970s living room with decent space around the unit and nothing stacked on top, that chimney effect was good enough for the 10 or 15 years most people expected a receiver to last. They never designed these machines to still be running strong in 2026. The physics, unfortunately, did not get the memo. 40 or 50 years of continuous thermal cycling has turned a workable compromise into a slow motion failure mode. What makes this especially sneaky is that the heat never takes a day off. You can leave the receiver powered on with the volume at 0 and the regulators will still be dissipating energy. I've seen boards where the fiberglass around the regulator section has darkened over the decades simply from long-term exposure. Solder joints nearby develop the classic fatigue rings. Thermal compound turns to powder. None of this requires loud music or heavy loads. The silent killer is already at work while the unit sits there looking completely innocent. That's why I now treat idle heat as seriously as any other aging factor. The convection system that was perfectly adequate in 1978 is simply outmatched by the calendar. 2. The stages of capacitor death and the quiet damage spreading. I've pulled enough old capacitors out of vintage receivers to recognize the pattern the moment I see it. The failure almost never happens overnight. It moves through clear stages, and heat is the force that pushes every stage along faster. Stage 1 is the most dangerous because almost no one notices it. Capacitance begins drifting downward and equivalent series resistance starts climbing, yet the receiver still plays music that sounds perfectly acceptable to most ears. In fact, some people even prefer the slightly warmer, softer presentation that comes with rising ESR. On the bench, I can measure the change, but if you just sit and listen, you would never know anything is wrong. This silent degradation can last for years. The capacitors are already compromised. They just haven't crossed the threshold where the ear or the protection circuit complains. Stage 2 is when the problems become audible. Bass starts thinning because the power supply can no longer hold voltage steady under dynamic load. High frequencies take on a grainy edge. A faint 120 Hz hum, or 100 Hz depending on where you live, begins to ride underneath the music. One channel may go soft or develop more distortion than the other, simply because the capacitors on that side of the board sat closer to a heat source and aged faster. Crackling that comes and goes with temperature is another classic sign. I've had customers describe it as the sound of bacon frying that appears only after the unit has been on for 20 or 30 minutes. At this point, the capacitors are still working, but they are working poorly, and the heat they generate from their own rising leakage current only makes the situation worse. Stage 3 is the dramatic end. A capacitor opens, shorts, or vents its electrolyte. You get loud hum, intermittent cutouts, repeated trips into protection, blown fuses, or that unmistakable burning smell. Sometimes the capacitor ruptures and sprays conductive goo across the board, corroding nearby traces and component leads. I've seen power supply boards where one failed electrolytic took out 2 transistors and a handful of resistors in the same event. Once you reach this stage, the damage is no longer limited to the capacitor itself. Heat accelerates every one of these stages. Capacitors sitting next to regulator transistors or power transformers routinely reach stage 2 or 3 years earlier than identical parts located only a few inches away in a cooler section of the same chassis. On a Pioneer SX 1250 power supply board, the difference is obvious. The small electrolytics nested between hot 220 packages are almost always the first ones to show, shrunken sleeves and elevated ESR, while the big filter cans farther away may still test with intolerance. The capacitors are not the only victims. Solder joints are quietly failing in parallel. Decades of heating and cooling cause the solder to work harden. Under magnification, you start seeing fine concentric rings around the component leads, classic fatigue marks. A joint that still measures fine at room temperature can open the moment the board reaches operating temperature and the metal expands. I've chased intermittent channel dropouts that only appeared after the receiver had been on for half an hour, only to find a single cracked joint on a driver board that looked perfect until it got warm. Transistors and regulators suffer the same thermal history. The white thermal compound that once conducted heat efficiently turns into dry, powdery residue. Once that happens, the semiconductor runs hotter than the designers ever intended, which shortens its life and raises the temperature of every nearby capacitor even further. Circuit board material itself becomes more brittle after decades of thermal cycling. Traces that held firm for 40 years can lift during routine desoldering simply because the bond between copper and fiberglass has already been weakened by years of expansion and contraction. I see all of these effects together on the same boards. The capacitors are drying out, the solder joints are cracking, the thermal compound is turning to dust, and the board is growing fragile, all driven by the same slow, relentless heat. The progression is predictable once you know what to look for. The only real variable is how much heat the particular design generates and how well the original convection cooling was able to remove it. In most late 1970s receivers, the answer is not well enough for another 20 years. 3. What forums and real-world owners report? I've spent more hours than I care to admit reading through Audio Karma, the various Facebook, vintage audio groups, and the older threads on DIY audio. The same stories keep surfacing, and they match almost exactly what I see on the bench. Owners talk about regulator sections that run hot enough to slowly darken the fiberglass around them. One guy posted clear photos of a Pioneer stabilizer board where the area near the TO220 packages had turned a distinct brown after decades of continuous heat. Another owner measured the top of his power transformer at over 140 degrees Fahrenheit an hour after he shut the receiver off. He said he could still feel the warmth radiating through the chassis cover. These aren't extreme cases. They're common. A lot of people eventually get tired of the heat and start experimenting. Some drop a laptop cooling pad on top of the receiver and run it at the lowest fan speed. Others scavenge quiet 80mm or 120mm PC fans, power them from a 9-volt or even 5-volt adapter, and place them to pull air out of the top vents or across the rear heat sinks. I've seen photos of neat little setups using the switched outlet on the back of the receiver so the fan only runs when the unit is on. Several owners who have done this for 3 or 4 years report that the chassis stays noticeably cooler and that they have had fewer intermittent problems since adding the airflow. Tube amplifiers show a more dramatic version of the same problem. The power transformers and output tubes create intense local heat that can cook nearby electrolytics and carbon composition resistors in a hurry. Solid-state receivers from the late 1970s are quieter about it. Their heat comes mainly from the linear regulators that are working even at idle, so the damage builds more slowly and more evenly across the power supply section. The end result is the same, just less obvious until you open the unit. The shared conclusion across almost every long thread is simple. Heat is the long-term enemy of these machines, and even modest, continuous airflow makes a measurable difference. People who added quiet fans years ago tend to post follow-ups saying the gear still runs cooler and more reliably than it did before. The ones who ignored the heat often come back later with photos of shrunken capacitor sleeves, cracked solder joints, or boards that needed far more work than a simple recap. If these real-world reports and the patterns I keep seeing on the bench are useful to you, and you want more detailed looks at actual power supply boards after decades of thermal stress, channels like Novolux Stereophonic are worth following. They show the exact damage up close and walk through the practical cooling approaches that owners have been quietly using for years. Why a full restoration is not enough, and the simple cooling fix that actually changes the long-term outlook. I finish a full restoration, button the chassis back up, and the receiver sounds better than it has in 40 years. Every electrolytic is new, 105 degrees Celsius, low ESR stock. Thermal compound is fresh. A few stress transistors have been upgraded to more robust packages, cracked solder joints have been reflowed, bias and DC offset are dialed in perfectly. On the bench, it measures clean and runs cool during testing. Then the customer takes it home, powers it on, the same way they always have, and the original heat source is still right there waiting. That is the part many people miss. A thorough restoration replaces the victims of heat, but it does not remove the heat itself. The linear regulators are still dropping voltage and turning the excess energy into thermal energy the moment the unit is switched on. Even at idle, the power supply section begins warming up. The new capacitors will last longer than the dried out originals. The fresh thermal compound will conduct heat better for years. The reflowed joints start with a clean slate. Yet all of those new parts are still living inside the same thermal environment that slowly destroyed the old ones. They will age more slowly, but they will still age. I have seen restored units come back 3 or 4 years later with early signs of the same stress. Slightly elevated ESR on the small caps nearest the regulators, the beginnings of fatigue rings on a few joints, thermal compound that has already started to dry at the edges. The restoration bought time. It did not rewrite the physics. That realization is why more of us who work on these machines now treat cooling as part of long-term reliability instead of an optional extra. The practical answer is simpler than most people expect, and it requires no invasive surgery. Almost every late 1970s receiver and integrated amplifier has a switched AC outlet on the rear panel. It was originally meant for a turntable or tape deck, but it becomes live only when the receiver itself is powered on. That single feature gives us a perfect automatic trigger. Take a small, ultra-quiet 1-2 volt DC PC fan, something in the 80 millimeters or 120 millimeters range with decent bearings, and power it from a 9 volt wall wart adapter plugged into that switched outlet. The fan only runs when the chassis is generating heat, and it shuts off with the receiver. Running the fan at reduced voltage drops the noise to a level most people cannot hear once music is playing, while still moving enough air to lower internal temperatures by a useful amount. I have measured drops of 8 to 15 degrees Fahrenheit in the regulator area on several different models after adding this kind of airflow. That difference compounds over thousands of hours. Placement is flexible. Some owners simply set a single fan on top of the cabinet, so it assists the natural chimney effect by pulling warm air out through the existing vents. Others prefer a gentle intake or a dual fan setup that creates light circulation through the chassis. A couple of zip ties or small brackets keep the power lead tidy so nothing dangles. If the room is dusty, a thin foam filter over the fan intake keeps the inside cleaner without restricting airflow much. The whole modification stays completely external. No holes drilled, no wiring altered inside the unit, nothing that affects originality or resale value. I have spoken with owners who have run this exact arrangement for 4 or 5 years. They report cooler chassis tops, fewer intermittent issues, and a general sense that the receiver is under less stress One person with a pair of high-power Pioneers told me the power supply section that used to be uncomfortably warm after 2 hours of listening now stays only mildly warm even after a full evening. The fans are quiet enough that guests never notice them. The beauty of the approach is that it attacks the root condition instead of only treating the symptoms. New capacitors and fresh thermal compound are still essential. I would never skip them, but pairing those parts with continuous, gentle airflow changes the rate at which the next round of aging occurs. You are no longer simply replacing what heat destroyed, you are reducing the heat that will try to destroy the replacements. That combination, proper restoration plus simple active cooling, is the closest thing we currently have to a realistic long-term strategy for these machines. The physics of linear regulation will always generate heat. We cannot redesign 50-year-old power supplies. We can, however, give the heat an easier path out of the chassis so the new parts we install today have a better chance of lasting as long as we hope they will. 4. Everyday habits that reduce thermal load. Other modest habits compound the benefit. Keep space above and around the receiver so convection can work. Do not stack a turntable or another component that blocks the top vents. Avoid enclosing the unit in a tight cabinet without additional ventilation. In warm climates or during summer months, even a small external fan directed at the rear heat sinks makes a difference. Power the gear regularly rather than leaving it idle for years. Electrolytics stay healthier when the oxide layer is periodically reformed by normal use. When storage is necessary, choose a cool, dry place rather than an attic or unconditioned garage. Looking across brands and designs, the same heat story appears across brands. Pioneer SX series receivers, especially the higher power models with complex regulated supplies, show the pattern clearly. Sansui G series units develop similar issues around their power sections. Marantz receivers of the era, while often praised for build quality, still rely on convection that was never designed for half a century of continuous thermal cycling. Even lower-powered integrated amplifiers eventually reveal the same capacitor and solder fatigue when the chassis has spent decades converting excess voltage into heat. Tube amplifiers face a more obvious version of the same problem, but the underlying chemistry remains identical. Heat shortens component life. I have seen boards where the only obvious clue was a slight discoloration of the fiberglass around a regulator. Under magnification, the solder joints told the rest of the tale. Owners sometimes bring in a unit that just started acting up, only to discover that the real damage began 10 or 15 years earlier, when the first small capacitors near the heat sources began their slow decline. By the time the symptoms become obvious, multiple components have already been compromised. That is the nature of a silent killer. It does not announce itself with smoke the first time it appears. It works quietly while the music still plays. The gear sounds fine until the cumulative effects cross a threshold, then the repair bill arrives, or worse, the unit is set aside because it no longer sounds right. Modern 105 degrees Celsius capacitors and better thermal compounds buy time. Thoughtful cooling buys more. Understanding that heat is the underlying driver changes how you treat the equipment day to day. A few degrees cooler over thousands of hours of operation can mean the difference between a reliable classic and a parts donor. The next time a vintage stereo powers on without complaint, remember the quiet work happening inside the chassis. Voltage is being regulated. Heat is being generated. Components are aging at a rate determined by that heat. A little attention to cooling can change the slope of that aging curve. For machines that already represent some of the best engineering of their era, that attention is often the difference between continued enjoyment and an unexpected silence. If the details about thermal stress and practical cooling help you keep your own gear healthy, subscribe to the restoration channels that document the real boards and the real fixes. The more people who understand the silent killer, the more of these machines will stay in service instead of disappearing into incomplete repairs or landfills. Heat will keep working. Awareness and a quiet fan can work against it.